Record. Hi, recording is rolling. It is Monday, January 30th, and I've got some textbook puzzles lined up for you guys today. We're just going to do as many as we can. We're just going to take all class period of these textbook puzzles. So, remind you guys what we did last week, how to tie into this, and where we're going with it. So, you guys remember last week, mostly talked about two things, reflection and refraction. So, you guys remember reflection? You have a plane mirror, you might have a curvy mirror. If it's curvy, it might be convex or concave. We're trying to figure out where the image is going to be. We did some ray diagrams, but we also did, there should be an equation on here. This one right here. One of the focal distance, one of the distance image, one of the object. Could also set ray diagrams for mirrors. Okay. Then we talked about refraction, Snell's law. Okay. You guys remember the lab with where's my laser? Okay. Laser, glass prism, the whole deal. Okay. And then back on Friday, we talked a little bit about color theory, additive and subtractive color mixing. You guys created Newton's wheel and Benham's wheel. All right. So that this is going to correspond. All these object topics are going to correspond to about 4 chapters in the book. And so chapter 16 is fundamentals of light. Let's look at this real fast. So here we've got some of the questions here are like new topics, right? So you guys are going to learn some new stuff today. We've got illuminance based on luminous flux. It has to do with like how bright is light? Like how do you measure how bright is light? Like in candelas, maybe. It's something we haven't quite talked about before. You might see some looks kind of like the Doppler shift because it is a Doppler shift, but it looks a little bit different from sound. You guys remember Doppler shift for sound, right? Depending on like, say there's a car that goes by on the street, what frequency do you hear? Well, are you in the car? Are you on the sidewalk? How fast is the car going? How fast is the observer running back and forth? What's the speed of sound through the air? Right? So it works a little bit differently for light. You guys remember light doesn't actually need a medium to travel through a vacuum. Like that. And then chapter 17 is your reflection. So, hey, look, we've got spaces for some ray diagrams and maybe some problems we can solve with some equations. We go back and forth between those. Magnification. Chapter 18, refraction. So now it's like Snell's law. Right? This sort of thing. Right? Oh, look, yeah, I see some refraction going on here. Okay. And chapter 19 is like interference and diffraction. We'll see how far it takes to get that one. Okay. So start here with number 56. I plan to do all these with you guys, or probably all of them. Right? Number 56, Earth speed. What's it about? We got Ole Romer found that the average increased delay and disappearance of Io from one orbit around Jupiter to the next is 13 seconds. What's that about? So I'll give you guys some context for this one. Number 56. Right. All right, so here's Jupiter. Okay. Big red spot, stripes. Okay, there's Jupiter, right? Now, with the conventional telescope, you can see basically 4 moons going around Jupiter. Now, Jupiter has some other moons too, but there's like 4 particularly big ones we can see. And these are like orbiting Jupiter. So let's pick one of them. Okay. And we're watching the thing go around. Okay. Now, what's kind of interesting is that as Earth is approaching Jupiter, it appears that this moon is going around Jupiter a little bit faster, right? Or you might say its frequency going around Jupiter is increased. Versus when Earth is going away from Jupiter, it looks like it takes more time for that moon to go around Jupiter, right? Or you could say it goes around like less frequently, right? Difference in frequency. That sure does sound like Doppler shift. Now, what they're getting at, I think this guy was a Dutch astronomer, I think, is this is actually one of the first ways, and it might be the first way, that the speed of light was actually calculated, right? Now, so a little bit complex, and your book actually takes you a little bit different way through the adventure because we're assuming we know what the speed of light is, and they ask you some other questions. But what he was actually trying to figure out is what is the speed of light? Because he realized that there could be this Doppler shift, and then if you can kind of estimate the distances of these things, you can sort of figure out what the speed of light is based on this change in frequency. Okay, so again, we're not solving the check for that, but let's just solve exactly what your book wanted you to solve, and you kind of do it backwards and kind of get back to the speed of light. So, question A. How far does light travel in 13 seconds? Well, since you guys know what the speed of light is, can you guys say that distance is equal to speed times time? Right, you guys could say that, right? Now we have a special speed, the speed of light. Let's say we know it because it's 21st century, and let's plug it in. Call it 3.0 times 10 to the 8, and that'd be meters per second. Okay. let's do that for 13 seconds. See, what is that distance in meters? 3 times 10 to the 8 times 13. Okay. I'm getting, whoops, 13. 3.9 times 4689 times 10 to the 9 meters. Right, would be one way to say it. Or you could call it, here, guys, 10 to the 9. What's another way to say that? It's not 1,000, it's not a million, it's a billion. Yeah, you call it 3.9 billion meters. Right? Or if you like, you could call it 3.9 million kilometers. Right? It would be another way to say it. So say you do those, they would all work. Okay. Part B. Each orbit of Io takes 42.5 hours. Right? So Io orbits Jupiter every about 42.5 hours. Earth travels the distance calculated in part A in those 42.5 hours. Okay? Find the speed of Earth in kilometers per second. And this is one of the problems where you gotta really just like sit down and think deeply about this. Let's say that the time change for Io going around is like 13 seconds. Okay, so we've got that difference. How far Earth would go around in, say, this amount of time. Right, so, and the unit that we're looking for is kilometers per second. Right? So, Earth goes that distance in 42.5 hours. So, part B. The speed of Earth then is this distance in kilometers, 3.9 million. Million is 10 to the 6, right, kilometers. Okay. And it does this all in 42.5 hours. Okay. Now, one more thing, it said they wanted it in kilometers per second. Guys, can you convert from kilometers per hour to kilometers per second? You guys remember dimensional analysis? I mean, we've done a ton of dimensional analysis in this class, right? This is one of those handy tools that just keeps coming up over and over, right? You can say like 1 hour is 60 minutes. 1 minute is 60 seconds. Right? Or if you like, you can go, there are 3,600 seconds in an hour. You can jump straight to that. Fine too. All right, so let's put this all in. 3.9 times 10 to the 6, right? 3.9 million. Right, that's kilometers. Right, divide by, open some parentheses. 42.5 by 60 by 60. Right, and then you guys have done plenty of dimensional analysis. Hours, minutes. You guys see we got kilometers per second on the board. Okay, that's why I set it up that way. Okay. And so I'm looking at 25.49, maybe I'll call it 25.5. How about that? Kilometers per second. Okay. Okay, so again, this is like knowing what the speed of light is. Okay, you can figure out, okay, well, Earth must be going that fast to perceive this effect. Okay. But there's one more thing here. We got a different perspective. Part C, check to make sure your answer is reasonable. Calculate Earth's speed using orbital radius and the time period of 1 year. That would be a more straightforward way to figure out what is the speed of Earth, like the tangential speed. So here's 56 part C. Okay. Let's get like a top-down view of Earth going around the sun. So here's Earth going around the sun, right? Okay. They tell you the average orbital radius. So that was, you guys have probably you might have heard this, right? Have you guys ever heard the sun is 93 million miles away from Earth, or 150 million kilometers? Okay. So we know that, okay, and we know it takes exactly 1 year to go around. So put those two ideas together. The speed of Earth is distance divided by time. Now, the distance, guys, what's the circumference of a circle? Is that 2 pi r? Right. Now, of course, you guys know it's actually elliptical, but it's pretty close to a circle, right? So we're gonna, okay. And the time period is 1 year. Right. You guys have done this several times before too. Right. You guys remember Play-Doh canisters and the PVC pipe? You guys were doing centripetal force lab way back in the day. Right. You guys used those then. Right. So 2 pi times 150 million kilometers. And this is all in a time period of, well, you could say 1 year, you could say 365 days. 365 days, or 365 and change if you like. Okay. But we need kilometers per second so we can compare these answers. So I'm going to add to the dimensional analysis table a bit here. Okay. I know that 1 day is 24 hours and 1 hour is 3,600 seconds. Hours, days. Now I got kilometers per second on the board. Okay. Part B, we calculated the speed of Earth with, from a different point of view, and the answer was the kilometers per second. So we can compare these two answers. Say, hey, how does this compare to that? Okay. Let's do 2 pi times 150 times 10 to the 6th. So that is the distance in kilometers that the Earth goes around the sun, circumference. Okay, divide that all by, open some parentheses, 365 days, 24 hours in a day, 3,600 seconds in an hour. I'm looking at 29.88, I'll call it 29.9 kilometers per second. Okay, that's the tangential speed of Earth that you see. Like we're outside observer watching it go around like that. Okay, now let's compare those numbers. So using this method, which is a bit more straightforward, we got 29.9 kilometers per second. Using the method of this old Dutch guy looking through an astronomer, we got, something extremely close to that. Right? And of course, way back in the day, like hundreds of years ago, when this experiment was originally done, he's saying, oh, hey, it's off by 13 seconds either way. See, he didn't know the speed of light. So what he could do is say, okay, well, we can kind of estimate the distance from the Earth to the sun using our best estimates. We can estimate all these other numbers. We can essentially do this all in reverse. So he was able to back calculate what the speed of light was. Okay. Right, and in the meantime, speed of light's been calculated in ways that are more accurate, and we're going to talk about that when we eventually get to relativity that we'll think about. Okay, number 57. Student wants to compare the luminous flux. Okay, here's a new concept. We're going to learn something new right here. Of a light bulb with that of a 1750 lumen lamp. Because if you go to the store and you buy a light, now, like a lot of light bulbs are listed in watts. Now, watts is really like the rate that it's pulling energy off the grid. Right? So like a power rating. But if you want to know like how bright is something, that's something that we haven't actually quite talked about in this class. I mentioned it very briefly, maybe like way back in August. I said there are like 7 fundamental ways to measure things, right? Like displacement in meters, time in seconds, mass in kilograms. Right? And one of them was like brightness and candelas. So let me pause right here so I can fill you guys in on some stuff, because there's 3 closely related concepts that every time before I teach this subject, I have to go back and revisit this. Wait, hold on, what's what again? Right. So luminous flux, luminous intensity, and illumination. I mean, it sounds like it could be 3 things interchangeably. And actually 2 of these things are like really closely related. You're looking at them right here. So luminous flux measured in lumens versus luminous intensity measured in candelas. Remember, candela was like one of these basic SI units, right? Well, really, these are like almost sort of the same thing. And here's why. There's like some brightness. Let's say you have like a candle, like, right? And you look at like 1 meter away from the candle. Okay. Well, how much light is like out like 1 meter away from that candle? And you could do that like from any like point source of light, right? And get how bright it is. You can quantify it in either way. Now, if you're looking at the entire shell, like the entire spherical shell, like there's some amount of light that lands on the inside of that shell, and you could quantify that in like some number of lumens, right? Or instead of that, what if you roped off like basically a 1 meter by 1 meter square, like that, and kind of wrap it around the shell? You can see how it would land like on part of this. Say, well, how much light lands on that? Right, and that could quantify it in candelas, right? Now, if you know how many candelas there are, you can calculate how many lumens just by scaling it up. Do you guys know how to find the surface area of a sphere based on its radius? Do you guys know? Like, suppose you have a ball, like a basketball or something, right? I mean, if you know the radial size of that sphere, it's like a shell. In principle, there is like some associated surface area, right? It ends up being 4 pi times that radius squared, right? So you take the radius, you square it, so you can get like a square area. That's like, imagine there's like a square right here, right? And then multiply it by 4 pi, and that'll scale up. They'll tell you the surface area. So it's 4 pi times the radius squared, right? So if you take like 1 candela, right? Here, guys, try to say calculator. Open up your calculator. Okay, take 1 meter squared to get 1 square meter, and then multiply by 4 pi. So basically, what's 4 pi, right? What does that come out to? You guys see 12.56 something. Okay. Hey, look, that's that number right there, 12.56 lumens. So one candela is the same idea as 12.56 lumens, right? You know, one near the other. You guys kind of get that? Okay. All right. But then there's a third concept, which is luminance, which is, well, if you back up further away, what if you aren't 1 meter away from the light source? What if you're like some other distance, like 3 meters away, right? Do you guys think the further away you get, like the dimmer the light appears to be, the less light you capture? In fact, this is something you guys have seen before. You guys remember we were talking about universal gravitation? You guys remember something like the inverse square law, right? So if you back up, for example, 3 times as far away, if you triple your distance from light source, how much light do you capture compared to the original distance? 1/9. Yeah, you guys remember that? Because it's like inverse square law. It's 1 over the distance squared. You guys remember that? Right? Right. And that's going to bring us back to this problem here. Well, it's pretty close related to this. Right, so we got these 2 light sources. We got this 1750 lumen lamp. Oh, yeah. So if you go to the store, especially a lot of bike lights, they're listed in lumens. So, okay, you want to know how bright? So many lumens, right? But we've got this light bulb, and it looks like we're illuminating the sheet of paper. Right? So from one side, we got the lamp. From the other side, we got the bulb. And they're equally equally as bright. Right? So if you're an ant crawling around on the paper, right, appears equally bright on both sides. But they're different distances away. That 1750 lumen lamp is 1.25 meters away. The light bulb is 1.08 meters away. And yet from the surface of the paper, they appear the same. Well, they must have different luminous fluxes then. What is the light bulb's luminous flux? Okay. So let me draw this out for you guys, and then we'll think about this and we'll solve this thing. So 57. So I got this sheet of paper. Hold it vertically. Okay. And on one side, I'm going to have a lamp. Okay. It's all bright. Okay. And on the other side, I have a light bulb. It's also lit up. Okay. Now, from the point of view of the paper, like right side of the paper is the bulb, left side of the paper is the lamp. Okay. They seem equally bright. But if you plug in the distances, this lamp is like 1.25 meters away. And this bulb is a bit closer, like 1.08 meters. Okay. So question for you guys. The fact that they appear equally bright from the point of view of this paper, right, which light source is actually brighter? Like if you're like equal distance, right? Which one's actually brighter? The lamp or the bulb? Like which one has greater luminous flux?
So the same.
Yeah.
The lamp would have a higher luminous flux.
Yeah, everybody says lamp, right? Everyone says lamp. Okay, all right. So, okay, here's the next thing. So whatever answer we get here, this is the lamp itself is 1750 lumens. Okay, the answer we're looking for has to be less than that, right? It has to be less than 1750 lumens. Okay. You guys see this question here? It says E equals P over 4 pi r squared, right? So E stands for illuminance, P stands for the luminous flux, right? So illuminance, of course, depends on your distance, and that's what the R is, right? The R is like your distance away, right? The important thing here is the inverse square relationship between the E and the R, right? And that's, I'm just going to cut straight to that inverse square relationship pretty much for this, because the illuminance is equal for both of these. So the E from the lamp is equal to the E from the illuminance from the bulb, right? It's the same illuminance on the paper, left side, right side. Okay. So the flux from the lamp over 4 pi r lamp squared is the luminous flux from the bulb divided by 4 pi r bulb squared, right? Okay. And then the 4 pi just like cancels out. So that immediately just takes it to the inverse square relationship, right? And we know 3 of those 4 things, right? Boom, boom, boom. There's 4 variables. We know there's 4 variables. We know 3 of those, right? Because we know the luminous flux from the lamp is 1750 lumens. Told us that. And the distance is 1.25 meters. Don't forget to square that. The flux from the bulb we're solving for. And the distance to the bulb is 1.08 meters. Don't forget to square that. You guys see we're one step away from solving this? Take 1.08 meters squared, cross multiply it. Okay, you guys that? So it says 1750 divided by 1.25 squared times 1.08 squared. Okay. Here, I'm just gonna write the answer out here. Okay. So flux from the bulb is, I'm getting 1306 lumens.
I got the same answer in a different way.
Oh, yeah.
It was 1.25 squared divided by 1.08 squared. Inverse that using 2 negative the first power to the negative first power, and then use that as the multiplier.
Oh, yeah, that'll do too. Yeah, all right. Yeah, a little bit out, different ways to shuffle the alphabet. All right, and yeah, it is not as bright as the line. Okay, all right, you guys got that? And so, I'm gonna mention is okay, over the weekend I did write a quiz for you guys on all the stuff we did last week and some of the stuff that you guys are gonna see today and tomorrow. We're gonna do as many as we can. And so I just need to get this to you guys next year. I think I'll make this like a take home quiz. Get this to you guys soon. Okay. But if I ask a question, anything about this, I'm mostly just going to focus on this inverse square type relationship. Like if you change your distance, how does that change the luminance, right? Sort of thing. Right? So really similar to a universal gravity question, right, from last semester. All right. Moving on here. Ooh, we got some stuff about spectroscopy. Number 14 through 17 here. Let me pull up something from the book here. All right, so do you guys see a poster up there? It says spectral lines. Okay, it's got it for a few elements, I think like first 8 elements. Right, so then here's kind of the version from the book. Okay, so every element will emit or absorb a little bit different parts of the spectrum. So you can do this in the lab, right? And then eventually we're going with a question like this is, say you're looking out at stars. If you want to figure out the composition of stars, they're like mostly hydrogen, some helium, and like trace amounts of other elements. How do they know that? Well, I can get this by using a spectrometer and pointing at the star and looking at these spectral lines, right? Call these like Fraunhofer lines, something like that. Okay, and then there's another thing you can do with this too, which is that if there's like a galaxy that's like moving away from us, you guys remember like Doppler shift, right? They'll actually be Doppler shifted, so the wavelengths will actually change a little bit, and then you can figure out like how fast these galaxies are moving away from us. Right, so that's a big picture idea. These next few problems we're doing here. So let's start real basic. Number 14. What is the frequency of oxygen spectral line if the wavelength is 513 nanometers? Okay, so they just gave us a wavelength and they're looking for a frequency. Hey, that sounds like speed equals wavelength times frequency, doesn't it? So let's do 14. Speed equals wavelength times frequency. Okay. Now it's a special speed of light, but that's all right. What's the frequency? So would frequency have to be speed divided by wavelength? It have to be. Okay. Plug in numbers. We got 3.0 times 10 to the 8 meters per second. Speed of light in a vacuum. And 513 nanometers. So I'm gonna write 513. Okay, guys, nano. Okay, nano is 10 to the what? -9, right? It's like 1 billion. Okay. Nano is like a billion. Right? Micro is a million. Nano is a billion. Okay. So that many meters. Okay. So this is within the visible spectrum. Right? Okay. So some hundreds of nanometers. So let's write that. I'll throw this in parentheses. Goes from the calculator. What is 3 times 10 to the 8 close parentheses divided by open parentheses 513 times 10 to the -9. That is 5.847, or I'll call it 5.85 times 10 to the 14. And then this has a unit. Guys, what's the unit that describes frequency? Like cycles per second, beats per second. That's called hertz. You guys remember hertz? Okay. 10 to the 14 hertz. There you go. Okay. All right. Okay, so that was a good warm-up problem for 15. By the way, if you ramp ahead a little bit, number 15 and number 16 look really similar to each other. Really similar terms here. Got hydrogen atom in a galaxy moving with the speed of 6 point something times 10 to the 6 meters per second. Now pause right there, because let's put this in context. You guys know the speed of light is like 3 times 10 to the 8 meters per second. This is like 6 times 10 to the 6. What is 10 to the 6 compared to 10 to the 8? Is that 1/100th, right? It's like 2 decimal places, right? So this is like 100th of the speed of light. Or if you like, I mean, 6 compared to 3, that's like twice, right? So maybe it's a little over 2% the speed of light. Okay? So these galaxies are like moving away away from each other at a little over 2% the speed of light. Okay. All right, emits a frequency with this many hertz. What frequency of light from that hydrogen atom would be observed by an astronomer on Earth? Ooh, okay. Did I tell you guys about red shifting and blue shifting? I know it's on one of these posters hanging above my head, right? So say you got some galaxies. There's one that looks kind of like this, right? Got some galaxies going on here. Some galaxies around here, right? And let's say these galaxies are like moving around relative to each other, right? So just to simplify this a bit, you could just have one galaxy in the center, like moving left to right, or some idea to like these guys moving towards each other, these guys moving away from each other. Right? Now, you remember, like if a car goes by, you think about sounds, got that Doppler shift, something about changing frequency, right? So the two galaxies moving away from each other, is that going to bunch the wavelengths together? Is it going to stretch them out? Stretch them out, right? So that would look kind of like this, versus the ones that are going together. It's going to be like, like bunched together, right? That's it. Right. Now, if you're looking through a telescope, that's going to manifest itself in terms of like light, right? If it changes the light a little bit, either stretches out or bunches together, that's going to either shift it towards the red or the blue part of the spectrum. Which part of the spectrum is this, the red or the blue? Stretch out, long wavelength.
That would be the red.
That is the red. It's called red shifting. Okay, this is the other. This is called blue shifting. Okay. Now, if you look up in the sky, right, you're looking at like galaxies all over the place. Almost all the galaxies we see from Earth are all shifted which way?
Red.
Red. Yeah, red shift. Right. In fact, the more they're red shifted, it tells you a couple of things. They're further away, and they're also traveling faster away from us. Right. To go hand in hand because of the cosmological principle, how the universe expands. Right. There's a couple of exceptions, like Andromeda Galaxy is blue shifted, so it's on a collision course with the Milky Way. It's going to crash into it someday, long time ago. But yeah, all right, so we're talking about red shifting here. All right, so yeah, that's numbers we're looking at here. Now, here is the Doppler effect for light. The observed frequency is the source frequency times 1 plus or minus b over c. Now, the plus or minus has to do with is it more towards the red or more towards the blue, right? In this case, the fact that this galaxy is moving away from Earth, okay? That's going to redshift, which is going to make the wavelength longer and the frequency lower, okay? And how do you make the frequency lower? By adding or subtracting right here. The observed frequency has to be less than the source frequency. You get there by subtracting, right? You see subtracting, okay? So let's do that for number 15. So I've got Doppler effect for light, the observed frequency is equal to the source frequency multiplied by 1 minus v over c. V over c. Let's do it like that. Let's plug in the numbers. Observed is, the source frequency was 6.16 times 10 to the 14 hertz. Okay. That'll give it a frequency, that'll give it a wavelength, that'll be within the visible part of the spectrum. And multiplies by 1 minus, that's a fraction here. Okay. They said 6.55 times 10 to the 6 meters per second. That's compared to the speed of light is 3.00 times 10 to the 8 meters per second. You can try this out. If you divide out this fraction, it's a little over 2%. Let's do this right here. Let's chunk it down. 6.55 times 10 to the 6 close parenthesis divided by open 3.00 times 10 to the 8. Yeah, that is 0.0218 something. You guys see it's a little over 2% right there. Okay. Now, 1 minus that is like 0.978 something. Okay. Multiplied by the original frequency, I'll just multiply it by the 6.16. That's going to tell me the observed frequency is 6.0255. That's too precise, but you guys get the idea. 10 to the 14 hertz. Okay. I might just say like 6.026 or 6.03 maybe. But if I had that much precision, I could say something like that. Okay, let's go back. Okay, we're good. Okay, now, question number 16 really goes hand in hand with that. I think question 16, there's a typo here because they say a galaxy moving with the speed of 6.55 times 10 to the 16 meters per second. Now, these two questions go hand in hand, except for like this is kind of a problem. Right, guys, what's wrong with 10 to the 16 meters per second? That's faster than the speed of light. It's like 10 to the 8, right? So, yeah, if that was intended, it's only because, I mean, okay, how the universe expands, it's like, here, let me try to just with my hands here. Okay. How the universe expands is like, so you got a bunch of galaxies here, right? And the space between them expands at a uniform rate. So if you get two galaxies far enough away from each other, they can move away from each other faster than the speed of light, but nothing is actually moving faster than the speed of light. It's just space expands between faster. Right? In that case, you would never actually see the light at all, right? You would never receive light information from those, right? Well, I mean, it's a little bit more complicated than that. That's what kind of boils down to, right? But we're going to take this to be a typo. Right? We're going to say times 10 to the 6, okay? It's supposed to be times 10 to the 6. So that would be this. We can kind of approach this from two different points of view. We should get the same answer. One point of view is we can take our answer from the last question and just say, well, speed is equal to wavelength times frequency. Okay. So now we're looking for wavelength. Last question was frequency. Now the new question is wavelength. And since I have frequency from the previous question, I can just plug that in. So maybe this would be like a fast way to do it. 3.0 times 10 to the 8 meters per second. Okay. And the observed frequency, which was the answer to the last question, that's why I saved these extra digits, 6.0255, 10 to the 14 hertz. Okay, that was the answer that was the observed frequency that we got from as the answer to the last question. Okay, let's try this out. 3 times 10 to the 8, close, divide by open, 6.0255 times 10 to the 14. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, times 10 to the 9, 10 to the 9, that may be like nanometers. So looking at 498 nanometers. Okay. Okay. Or alternatively, you could use this stuff up here. So the difference in wavelengths, let's say the observed minus the emitted wavelength, is plus or minus b over c times the emitted wavelength. Now, if you do a little bit of algebra shuffle with that, you can actually show that it looks really similar in format to the Doppler shift for just frequency. Here, I'll show it to you guys. So the observed frequency, or sorry, the observed wavelength. Okay, I can just take the source, the emitted wavelength, add it over. So the emitted wavelength plus or minus b over c times the emitted wavelength. Then I could factor out the emitted wavelength. So observed is equal to emitted times 1 plus or minus b over c. And right there, doesn't that look the same structure as the frequency? Right? Okay, it's probably more convenient just to think about it like that. Right? Since we already got the answer, I'm just going to plug in the values that they gave us right here. Do this real fast. We should get the same thing. So the source wavelength they said was 4.86 times 10 to the negative 7 meters. Okay. The fact that it's moving away means now I have to say plus because I need to make the wavelength longer. Right, that's what redshifting is. Right. It's going to lower the frequency but increase the wavelength. Okay. And then let's do 6.55 times 10 to the 6 meters per second. Remember, I'm assuming that's a typo there. Not 16, but 6 as the power, compared to 3.0 times 10 to the 8 meters per second. Okay, let's see if it's good. Same thing here. Okay. Got 4.86 times 10 to the -7 meters. Got 1 plus 6.55 times 10 to the 6 over open parentheses right here. 3 times 10 to the 8. Going on here. All right, then times 10 to the 9 to get nano, creating prefix nano, and I'm getting the observed wavelength is 496.6 rounds to 497 nanometers. Okay, so the other way we did it, we got 498 nanometers. The new way doing it, we got 497 nanometers. Right, pretty much the same thing. Okay, guys good there? All right, and there's one more in this chapter, and this is number 17. Astronomer looking at the spectrum of the galaxy finds that, or so he's looking at a specific oxygen spectral line, and it's 525 nanometers. But back in the laboratory, the lab value said it should have been 513 nanometers. And it should have been 513, but it's too long. That's 525. Is that redshifting or blue shifting? Yeah, that's redshifting because it's too long. It's been stretched out, which means this galaxy is going away from us. So figure out how fast it's going away. Oh, and then also, is it going away or towards? But you guys just said it have to be away because it's redshifting. So we actually just, you guys told me that one. Okay. But now we just have to quantify how fast. Do that. So let's pick up from, okay, the last thing I wrote was a good place to start. This right here. So I took this, just some algebra rearrangement, got this. Let's pick up from that point. So number 17. The observed wavelength is equal to the source wavelength times 1 plus, yeah, I'm gonna say plus for this one. Okay. B over C for redshifting. And we're solving for this V, and we should know everything else. Okay. So they said, I'm plugging the numbers first on this one. Okay. We observed 525 nanometers, but in the lab it says 513 nanometers. 1 plus B that we're solving for compared to 3 times 10 to the 8 meters per second. Like that, right? And after these set up. Okay. The rest of this is algebra. So I'm going to divide the 513 over the nanometers cancels. Okay. So I got 525 on 513. So I'm going to divide that over. Then I'm going to subtract this 1. Then I'm going to multiply that all by 3 times 10 to the 8 meters per second. Just did a few algebra steps there, right? But you guys have done so much algebra in this class at this point. Okay. See how? Divide that, subtract that, multiply that. Boom, boom, boom.
It's about 7 times 10 to the 6 meters per second, right?
Ooh, that sounds right. Yeah. Let me confirm it, but I think you're right. That does sound right. 525 over 513, all minus 1 times 3 times 10 to the 8. Okay. Yeah, 1, 2, 3, 4, 5, 6. There you go. There you go. 7.0. About 10 to the 6 meters per second. Okay. Which is kind of in line. I mean, that's again pretty close to 2% of the speed of light. Pretty close to. Okay. There you go. 2% of the speed of light is gone. Guys up there? All right, so that covers chapter 16. There were some new topics there. All right, we got luminous flux and illuminance. We got Doppler shift. We got spectral lines. All right, so you guys got to learn some new stuff today. Okay, and then all right, next chapter's here. It's like last week's stuff, so you guys should be good on this. But you guys do this anyway. We got law of reflection, the reflected angles, the angle of incidence. So that's for reflection, right? We got this formula for where's the image compared to the object using the focal line distance of the mirror. Magnification, right? What's the height of the image compared to the height of the object? That's what magnification is. Number 54, a ray of light strikes the mirror at an angle of 53 degrees to the normal. What is the angle of reflection? You guys can stay a step ahead of me, then that's awesome. You know how to do this. But I'll draw that for you guys. Go. Mirror, normal line, 53-degree angle from the normal right here, 53 degrees. Then it bounces, boing. Guys, if that's 53 degrees, then what's that angle right there? 53 degrees. That's the law of reflection, right? Boing. There's your light ray. I should have changed the color with that. Like to see my light rays and light. There you go. Question B. That was A. Question B. What is the total angle between the incident and the reflected ray? What's this whole thing? 106. 106 degrees. Boom. Boom, boom. There's A, there's B. Okay. Guys go. 71 jeweler's mirror. A jeweler inspects a watch with diameter of 3 centimeters by placing it 8 centimeters in front of a concave mirror with a 12 centimeter focal length. Where will the image of the watch appear? And what is the diameter of the image? So that is this concave mirror right here. There's a concave mirror. It's gonna blow up your face. Isn't this? Okay. In this case, a watch. Okay. How? Where is the image and how big? So there's two ways we can solve this. We can use this formula right here, and we can also use a ray diagram. So let's try the formula first. How about that? So we do 1 over focal distance, 1 over distance image, plus 1 over distance object. Okay, we got 12 centimeter focal length, and that's 8 centimeters in front. So 12 centimeters here, 8 centimeters here. Whoops. I got my eyes mixed up. Okay, you guys get the idea. All right, so we're trying to figure out where's the image. What's the distance of the image from that mirrored surface? Okay, so I'm gonna subtract over 1 over 8 centimeters, so 1 over 12 centimeters minus 1 over 8 centimeters. Then, if you take the reciprocal of that, that will give you the distance of the image. So 1 over 12 minus 1 over 8. Okay, and I'm getting negative 24 centimeters. Now, the fact that it's negative, actually, I should ask guys before I thought, the fact it's negative means it's a virtual image. The image appears to be on the opposite side of the mirror, which is what we should be looking for if we're trying to use the concave mirror to like blow something up big. That's what we would expect. All right, last thing we'll do today, go back and solve this with a ray diagram, which we did last week. We got mirror, 12 centimeter focal distance, 8 centimeters to the object, which I'll watch right here. Okay, let's do ray diagram. So ray parallel goes boing, bounces to this focal point, appears to have come from back here. Ray that goes like this, goes to the mirrored surface. If I stretch my mirror up here, do this a little bit. Okay. It's going to boing, bounce this way, appears to have come from back here. And where those two rays converge, there's the image of the watch there. So do you guys see how here it's a virtual image that appears to be like way back in the page? Okay. And the other question they said is like how big is it in comparison? Okay. We're gonna do magnification is the ratio, distance image over distance object. So guys, what's absolute value? They throw it in a negative sign. Guys, what is 24 divided by 12? That's 2 times, right? So it's 2 times magnification. And if the original diameter was 3 centimeters, right? What's 2 times 3 centimeters? 6 centimeters, right? And the ray diagram pretty well agrees with that, right? You guys see that? This looks like 6 centimeters compared to that 3 centimeters, right? All right. Bell's going to ring in just a few seconds here, though. So that's going to have to be a pause point today. But we'll do some of these tomorrow, and then get you guys take a quiz here pretty soon. All right, guys, have a great rest of your day.